Hello, my name is Ingu Choi from Electrical Engineering Korea University. Today, I talk about hand tremor and EMI filtering using deep neural network for handheld microsurgery robot. Before I start the presentation, I will explain the handheld surgical robot. Surgical robots include teleoperative based surgical robots that are widely used around the world, such as Da Vinci, which can perform sophisticated tasks by teleoperating the robot remotely, but has the disadvantage that it cannot feel direct force is it is very expensive. A new robot that can overcome the limitations of conventional surgical robots is the Handheld microsurgical robot. Although this robot has a small workspace, it has the advantage of being able to feel the direct force and running time to operate is very short. If you look at the video on the right, you can see the surgical tool in hand. This surgical tool contains 6 degrees of freedom, parallel manipulator, and can compensate for hand tremor of the surgeon. When the function is the off, it can be used like a general surgical tool, and when the function is turned on, the manipulator moves and you can see how the end effector is fixed. By utilizing this function, you can implement the active tremor cancellation function, which can compensate the doctor's hand tremor in real time. There are two main problems I have defined. The first is noise caused by hand tremor, and the second is EMI noise. The first problem is the handheld robot should be operated by a doctor by hand. In other words, it is very important to remove the hand tremor of the doctor because it is away from the ground unlike other surgical robots. Even if doctor operates a surgery, a doctor's hand tremor occurs on the order of several hundred micrometer, and it is out of the scale of about 5-10 micrometer required for microsurgery. The video in the upper middle is a video of drawing a circle with a surgical tool. The person is working on drawing a circle with a size of 500 micrometer, but due to hand tremor, it is showing a shape that cannot be distinguished as a circle. The second problem is controlling a handheld robot requires the use of sensors that can estimate the handheld robot's position and orientation. Sensors that can estimate 6 DOA poses are mainly IMU, optical tracking, and electromagnetic tracking system. We will achieve 6 degrees of freedom using an electromagnetic tracking system that overcomes the limitations of IMU and optical tracking. However, as the BLDC motor is driven, inside the handheld robot, EMI is generated. This EMI significantly reduces the accuracy of the electromagnetic tracking system. The video in the lower middle shows the floating position of the tracker sensor. When the motor is driven, it can be seen that the sensor's position value contains high frequency noise. These noises are problems that must be addressed because they significantly lower the control accuracy of the microsurgery robot. This study is summarized as follows. There are existing tracking systems such as IMU and optical tracking that can be used in handheld robots, but electromagnetic tracking system that can overcome the limitations of existing tracking system is used. However, when used with an electric actuator, EMI noise is generated and the positioning accuracy is reduced. And many filters that can remove hand tremor have been studied, but there are no ways to remove it along with EMI. Therefore, this study aims to design a filter that can simultaneously handle tremor and EMI as a deep neural network for handheld robot manipulation. In order to drive the handheld robot, it is necessary to perform coordinate transformation between multiple coordinate systems, filter design, and inverse kinematics and motor control. Block diagram can be divided into two sections. It can be divided into the light blue area, which is the area for manipulating the handheld robot, and the green area for filters to generate the control input of the manipulation. In this study, we propose learning-based filtering for stable manipulation of handheld robot in the LED area. So this is my proposed idea. Let's extract only voluntary motion using LSTM neural network from the input sequence with voluntary motion, hand tremor, and EMI noise. The basic structure of a deep neural network is as follows. Construct sequence data with input data of noise position x, y, z values including voluntary motion, hand tremor, and EMI. It passes through the deep neural network and outputs a sequence which is a voluntary motion position data from which hand tremor and EMI noise have been removed. The structure of my proposed neural network is as follows. If you look at the structure on the left, 90 LSTM layers and 90 pi LSTM layers are arranged to provide a total of 180 hidden layers. A LSTM neural network was built through fully connected layers and regression. Uh, it was designed using field for removing phase delay as ground truth. When performing microsurgery, voluntary motion usually occurs below 2 Hz. In addition, it was designed with 3 other cutoff frequency of 2 Hz to remove hand tremors occurring in the between 6 and 40 Hz band, and EMI noise mainly occurring in the high frequency band. In order to minimize the loss of the neural network, the input sequence data is also designed with 3 other cutoff frequency of 2 Hz. And as a result, we can build data with only the phase delay difference. The dataset for training is as follows. A total of 442,006 data samples were collected at 500 Hz. This dataset includes when the motor is driving and when it is not, and 80% of them were designed as training sets. Hyperparameter is the same as in the upper right, and while learning is in progress, loss and RMSE error are attached to the lower right figure. The experimental environment for hand tremor and EMI filtering is as follows. After holding the handheld robot in hand, the manipulator is operated to generate EMI. Perform the task of pointing a dot with the tip of syringe under a digital microscope. The manipulator's G-sweeping was repeated 3 times for 20 seconds while changing the displacement and period. This is the experimental result. Time and frequency domains are analyzed. The position values are extracted for each XYZ axis. As the baseline, a low-pass filter designed with a third-order cutoff frequency of 2 Hz was set. The blue line is the low signal, the orange line is the ground truth, the yellow line is the predictive value, and the purple line is the baseline. Metric in time domain adopts RMS error. It was repeated 3 times in total, and the RMS error values of each signal were summarized in a table. For the x-axis, the result was about 3 micrometer, and it can be seen that the accuracy was improved when compared to the baseline. However, for other axes, the accuracy did not improve much when compared to the x-axis, as offset occurred. When viewed in the frequency domain, it can be seen that the filter design through the neural network is similar to the baseline. This paper is summarized as follows. First, we implemented a filter that can remove hand tremor and EMI noise at the same time. Second, it has high accuracy about the x-axis. Third, data pre-processing was performed to minimize loss. As our future works, we will increase the accuracy on the y-axis and z-axis and learning the orientation data and implement for learning-based manipulation. Thank you for listening to my presentation.